Hi all, in this class we are going to find the inductance of two-wire transmission line. In previous class we studied how we can find the capacitance of two-wire transmission line. So to find the inductance of two-wire transmission line, first we need to assign a suitable coordinate system. Then we need to provide a current I to that conductor. Then due to this I, there should be a magnetic flux density, and we need to find this magnetic flux density either using Biot-Savart's law or the Ampere's law. Then after finding this flux density, we need to find the flux associated with the circuit. Then we need to find what is the total flux. Then the total flux divided by current in that circuit is the self-inductance of that conductor. So next, now we can find the inductance of two-wire transmission line. So in figure we can see the transmission line consists of two parallel conducting cylinders with radius A each, and the separation between them is given as D here, and the conductor A carrying current I and the conductor B carrying current minus I. That means parallel wires, one is in forward direction, conducting in forward direction, and other is in backward direction. So first we need to find the magnetic flux density. So we can use either Biot-Savart's law or Ampere's law to find this magnetic flux density. So here we are using the Ampere's law. So to apply this Ampere's law, first we need to assign an imaginary path. So here also we assign our geometry is in the form of cylinder. So we are assigning an imaginary path in the form of circle. Then according to this Ampere's law, the line integral of H dot dl equal to I, and if we have n number of turns, then we can also write it as the line integral of H dot dl equal to Ni. So from this we can replace H as mu, H as B by mu. So you will get line integral of B dot dl is equal to mu I. So that's the relation between B and H. B is equal to mu H. So we know that the line integral of B dot dl is B into mean circumference of our imaginary path. So if the imaginary path have a radius r, then the mean circumference is B into 2 pi r. Then B into 2 pi r equal to mu I, or B is equal to mu I by 2 pi r. So after finding B, we can find what is the flux associated with the circuit. So to find the flux associated with the circuit, we are considering a small strip. So we can see the cross section of our transmission line in figure. So it consists of two conductors having radius A each, or the diameter is given as 2A each. So one conductor will conduct in forward direction and other conductor will conduct in backward direction, and we can also see that the center to center separation is D also. So to find the flux associated with this circuit, first we are finding flux associated with the small circuit, then that result we are going to integrate from A to D. That means from this one cylinder to another cylinder. So for this we are considering a small strip having length L and this width is dr. So the area associated with the strip is LdR. So the flux is B into dA. So we can replace it as B into LdR. So next we need to find the total flux lambda. So we need to integrate this result from A to D. So here we have two conductors. One conductor is conducting in forward direction and the another conductor is conducting in backward direction. So due to this two currents, we have the total flux density is 2 times of this integration of B to B dA. So you should remember that here we have two conductors are there. So the total flux due to these two conductors we need to consider. That means the flux due to first conductor plus flux due to second conductor. That means twice the flux. So we can find the total flux lambda as lambda equal to 2 times integral B dA. So the difference between the inductance to find the inductance in coaxial cable and this transmission line, the difference only is that in coaxial cable we have only one conductors. So the integration is only the integration from A to D B dA. But here we have two conductors are there. So the integration is 2 times integral B dA. So lambda is equal to 2 times integral b dA. So which is equal to 2 times integral from a to d mu IL by 2 pi r dr. So here we are integrating with respect to dr. So mu I by 2 pi L is constant. So we can take it outside. So 2 times mu I L by 2 pi integral from a to d 1 by r dr. So the integration of 1 by r is log r. Then give the limits a to d. Then you will get it as 2 times mu I L by 2 pi log of d by a. So that the total flux is 2 and 2 cancel. Then which is mu I L by pi log of d by a. So the only difference in coaxial cable and here is that in coaxial cable our expression for lambda is mu IL by 2 pi log of d by a. Here is mu IL by pi log of d by a. So to find the self-inductance, our expression is total flux divided by current in the circuit. So lambda by I. So we can write it as L is equal to mu IL by pi I log of d by a or mu L by pi log of d by a, or inductance per length is mu by pi log of d by a. Unit is that much Henry per meter. So mu by pi log of d by a is the self-inductance associated with a two-wire transmission line.